Hello and welcome back to Calculus 1, Section 2.4, Infinite Limits. So we're going to talk about right after this, Section 2.5, Limits at Infinity. So we're going to distinguish between infinite limits and limits at infinity. It's not a play on words. It's actually 2.4 is when answer is infinity, and 2.5 will be when you are actually approaching infinity. So they're completely two opposite concepts. So we are talking here about limit as x approaches a finite number. So x goes to c, you can also put a, whatever, of a function to give you either positive infinity or negative infinity. That is what we are talking about. So infinite limit means the answer is one type of the infinity, either positive or negative infinity. I can give immediately an example of that as limit x approaches 0 minus. What is the meaning of that? From the left. Very good. And if you look at the graph, right, it's going to be negative infinity. Also, limit x approaches 0 plus, which is from the right, the answer is going to be positive infinity. We don't usually put the plus there, but yeah. So how do we know that? Well, we just look at the graph, right? Use our eyes. And there's the answer. So technically, that's it. We're done. Now, does the overall limit exist in this case? Why not?
They don't match.
They don't match. So this is by the theorem. Theorem 2.2 from last class. Now you say, what's the theorem 2.2? You have the book. So this is it. Now, what else do I have? What's limit at 0 as x for 1 over x squared? What's limit at 0 from the left for ln x? What is limit for x goes to, for tangent x, x goes to pi over 2 from left to right? Or cosecant or secant. So all I get to do now is to change functions. That's all. I don't have conceptually, in terms of infinite limits, anything else. If you understand the concept that as you are approaching the finite number, like 3 or pi over 2, you are getting one of the infinities as the answer. That's it. All right? Now, talking about the major application of this and applying it is just a little bit more. And that would be the concept of the vertical asymptote. So for the first time, you're actually seeing the definition for the vertical asymptote. I'll just say vertical asymptote. So, vertical asymptote occurs when the limit at c is either positive or negative infinity. That's it. So, VA occurs when limit x goes to c. I'll put plus minus, so left or right, doesn't matter, of the function is one of the infinities. That is the definition for the vertical asymptote. Now, let's see. Immediately an example. Limit of 1 over x minus 5 as x approaches 5 plus is equal to what? So now we have to graph this. What is this minus 5 going to do? Exactly. Some of you said, actually, well, in your case. So shift it to the right. So we are going to draw 1 over x there. So now, if you approach from the right, you see that the answer is positive infinity. This means vertical asymptote at x equals 5. That's what it means. So I understand that you memorize the rule in pre-calculus, which says set the denominator equal to 0, and then whatever you get is the vertical asymptote. It's not all of its story. That's not a definition. That's one of the ways to get it, and in some cases it can get you in trouble. This is the definition for the vertical asymptote. So your exam question might look like this. Show that there is a vertical asymptote at 5. See? So can you answer that question as asymptote is at 5? Because the question states, show that there is a vertical asymptote at 5. How do you show?
You graph it.
You do this. That's all you need to write. Do this. Because you show by calculating the limit. And the limit calculation came out to be positive or negative infinity. This is calculus. The figuring out that there is a vertical asymptote at 5 can be done in pre-calc, but as I said, it's not all of the story, and we'll see that very soon. So when it says show, and the asymptote is given to you and everything, you crank the limit to technically prove the claim. Is there a VA for f of x equal ln x? Right? Now you all know how the graph looks like. Looks like this. So you would say, well, it looks like that there is one at 0. So let's check limit x approaches 0 plus, because it's approaching from the right, of ln x is equal to negative infinity. Yay! That means VA at x equals 0. That's it. Be very careful, guys, at the notation. This carries no points. This has no meaning. VA equals 0. Because VA equals 0 is not an equation. X equals 0 is equation. Y equals 0 is equation. VA equals 0 is nothing. So don't do that stuff. This is equation, that's equation, so this is the vertical asymptote, horizontal asymptote, and so on. So you have to use correct notation for these kind of things. It's time, it's calculus, right? There's another 20 years of math after this. I know. The NJT calls the courses Calc1, 2, 3, differential equations, elementary mathematics. That's it. Elementary. And then you have 20 years after that. Well, at that point, 18 years. Okay. What else? How about VA for, so vertical asymptotes for f of x equals x minus 5 over x squared minus 25. Do we have any vertical asymptotes? Yes. Okay. The answer is yes. Let's not prove anything yet. I want to ask another question. F of x equals to x squared minus 25 over x minus 5. Any vertical asymptotes? No. Nice. Usually students get this wrong, but this is good. You got it. Is anyone interested? Why? How? Yeah. Because you're used to denominator equals to 0. Let me ask a question. How many vertical asymptotes in the first question? One. One vertical asymptote. And let me just ask, x minus 3 over x squared minus 25, do we have vertical asymptotes? How many? 2. What the hell is going on? What the hell is going on? Yes, and then 1, and then yes, and then 2. It's the same denominator, right? You can see how pre-calculus 1 doesn't help here at all. You have to know definition for Calc 1. Yes? So now let's talk about this. All pre-calc 1 can do is give you candidates for asymptotes. And then calculus definition, the one with the limit, will determine which ones do we keep and which ones we throw away. So in the eyes of pre-calc, the candidates are 5 and negative 5 for the first one. But then when you factor and cancel, you see that only one survives. On the second one, if you factor and cancel, there's no more denominator. Now, function is still not defined at 5, so, and there's no vertical asymptote, so what has to be there? Open circle, yes, very good. So, this one over here, the last one, with x minus 3, will have both asymptotes at negative 5 and positive 5. So that's what's happening. Now, let's use calculus on all 3 of these problems. So I should have called them different. So yes, we have 1 and then 2. All right. Oh, actually, I don't want to do that because I want to call them 1, 2, 3. Problems 1, 2, 3. And we're going to take a look at them. We'll see. Actually, let me write. We have 1. No, we don't have any, obviously. And we have 2. All right. So let's work all of these out. So when you are faced with a problem like this, you say limit of x minus 5 over x minus 25, x squared minus 25, right? Not limit, f of x is equal to that. So that's number 1. And we set denominator equal to 0 to find candidates for asymptotes. Now that's going to be x minus 5, x plus 5 equals 0. So x is 5 and x is negative 5. So in pre-calculus, we are careful not to ask a question like this, right? Because you get in trouble. You don't have a limit, so you can't judge. But now you can. We have 2 of these. And you say, all right, the first one I have to check is the limit as x goes to 5. Pick left or right, it doesn't matter, from the left. For x minus 5 over x squared minus 25. Now, you know how to solve limits from last class. You when denominator is 0, you have to factor, rationalize, perform some witchcraft, whatever you can. So in this case, it's factoring. This cancels, and you end up with a limit x approaches 5 from the left for 1 over x plus 5. Now you know what kind of graph this is. It's a 1 over x graph shifted to the left, 5 units. So looks like this. Oh, wait, hold on. We don't need this. Because 5 plus 5 is what? Yeah. Now, this is, I'll spell it. This is not infinity. So, x equals 5 is not VA. We learned that if you get infinity, only infinity, positive or negative, then it's a vertical asymptote. But look what happened. We took the candidate for asymptote, we plugged it there, and we got 1 over 10. So it's not an asymptote. Now we do negative 5, and we will get infinity, so that one will be asymptote. So we're doing the same thing again, except x approaches negative 5 from the left. Writing this limit in front of the fraction is 5 points per step. And now look what we get. So now if you plug in negative 5, you get 0, so you have to graph and check. So shift it to the left. And as you are approaching from the left, we're getting negative infinity. So yes, VA at x equals negative 5. So I'm going to review this problem one more time from scratch. That's problem 1, and then we're going to do problem number 2. Go back to the top. We are considering function f of x equals x minus 5 over x squared minus 25. So we know from pre-calculus to set denominator equal to 0, that will give us a list of all possible vertical asymptotes. So that's just candidates, all right? We got negative 5 and positive 5. So pick the first one and do the limit. If you get a finite number, you throw it away. If you get infinity, it's an asymptote. So in our case, we use the 5. We canceled, we got 1 over 10. Because it's a finite value, it's a point. It's not an asymptote. Then we did the same thing, except now with the second number from the list, which was negative 5, and we got negative infinity. So that means that we do have vertical asymptote at negative 5. And that's it. So now we go with the second problem. The second problem was this thing flipped. So that's a terrible 2. There we go. So f of x is equal to x squared minus 25 over x minus 5. Again, take your pre-calculus, set this equal to 0 denominator, and you get x equals 5. So you would like to check limit as x goes to 5 for x squared minus 25 over x minus 5, which is the limit. X goes to 5, x minus 5, x plus 5, divided by x minus 5, cancel, and we get positive 10. Not infinity. So no VA. This problem has no vertical asymptotes of any kind. how does the graph of this then look like, right? It looks like just x plus 5 graph with a hole. So this is how it looks like. So that's the 5 on y, and there is an open circle at 5. So this is 5, 10. This graph that looks terrible over here, right? It's like, whoa, what would graph of that look like? That's it. It's a linear line with a hole at 5, 10. That's open circle there. No vertical asymptotes, no curves, nothing. It's just a linear line. And this is now also where you start understanding the power of calculus over pre-calculus. You're looking at this and you say, well, couldn't I just cancel this right away and don't worry about it? And the answer is no, because the actual graph that was given to you by application or whatever it is this, and it has a hole. If you just cancel them, then this hole will be plugged. Because then, if you just look at a problem, it will be f of x equals x plus 5. That has no holes in it. It's a single piece of the line going forever. But if you write it this way, it does have a hole at 5, 10. That value does not exist. Calculus is able to detect that. Pre-calc, no. Yes?
I'm a bit confused because let's say that graph represents an actual application. Obviously, calculus versus pre-calculus, but pre-calculus teaches us that we could easily just factor out the bottom part becomes 1 as we have in the equation there.
Yep.
Why doesn't that work in real life?
Because the applications, right, in a physical reality, certain things cannot be attained. I'll show some of the applications at the end. But, for instance, if a bridge is broken, right, you're looking at this long bridge. And there's a section missing, right? So just enough so cars can pass, all right? So the both parts of the bridge are standing, and let's say 2 feet. It's missing, but as you're looking at a very long bridge from side, you can just see it as a point, all right? The calculus is the one that solves that problem because as workers, right, we are going to approach from the left and the right and work and work and work and plug it, right? So that's the point. The pre-calculus equivalent of that would be what? It's like when Apple computer breaks. You just, what? It's garbage now, right? Because there's no fixing it, right? Well, actually, you can fix it for $7,000. But the idea is when you have a pre-calculus does not exist concept. That's it. You can't compute the value. You can't infer what it is. That's just end of the road. But in calculus, it's you have the limit, so you can approach and you look at all the values around it, and you can get there and at least know, if you can't fix it, you at least know what it is.
So when we do these kind of problems, we be very careful to, when we're factoring, if we're factoring out anything, make sure we still look at the original problem, look at the original denominator, just find out what the limit is.
Yes. So when you are looking at this graph is exactly x plus 5, but with a hole, right? So that's the difference between the, if you are to cancel here before you do any of this analysis, the graph would not look like this. The graph would not have this. And if this was obtained from a physical application, then it's, and unfortunately, you don't get to appreciate limits all the way to differential equations, actually. You're going to use limits heavily in Calc2. Heavily in Calc2. So we're going to use limits to define derivatives, to define integrals, and pretty much not talk about them at all in Calc1 after this, all right? But then in Calc2, there will be 2 chapters that will just be limits, 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 limits. And then Calc3, barely, and you go into differential equations, and then depending who's teaching it, the person might or might not show the true power limit. Because I'll give a quick example. You work out differential equation for population, and you get that population model that people always talk about, which is initial population is equal to e to the kt. right? So that's the initial population. So we're going to see this in Calc1. So when you get this in differential equations, you know that this is a bad model for population of humans or rabbits or whatever. Because the limit of this thing is going to go to infinity. And you know you can't have infinite population. Physically, you can't. It's a finite planet, finite resources, finite everything. So you have to have a different type of population. So you don't get to appreciate limits, you don't get to appreciate much of this stuff until it's actually used. And that's going to be later on. So when you're looking at these problems, we are now heavily upgrading that pre-calculus 1 notion of, yeah, we could have just canceled and then have the x plus 5, which we can clearly see x plus 5, but the actual graph is different from x plus 5 because it has a 0 there, and it has a 0 there because it can't be defined at 5. This graph has to be broken at 5. So it is x plus 5, but it has to be broken at 5, and this is the only way to write it. Yes?
So if you were to just graph the equation, like without all the factor that we listed and like all the canceling out, like why would it be an open circle versus like a line? Like why would the canceling out like affect the graph like that one?
That's exactly what I just said. If you are looking at the original problem, can you plug in 5 and compute in pre-calculus? And the answer is hell no, right? You plug in 5, you get 0 in denominator. So that's why it must be open circle at 5. It must be. Now, depending on how the function is, this could be x cubed minus 125 over x minus 5. In that case, it will be some kind of curvature, which will still have hole at minus 5. Because that one you can still cancel, but there is a quadratic that stays behind. And that quadratic will have a 0 on 5. Which goes back to, can you solve every single problem? Can I show every single problem? And the answer is hell no. This is what you do. You go home and you say, okay, so how does this problem now modify? What do I do if it's cubed? What do I do if it's d8? What do I do, right? And only one, and you will see the pattern that no matter what this is, as long as it has x minus 5 in it, to cancel, there will always be a hole, and whatever is left over after cancellation is the graph that you draw. But you draw every single one of those, right? And you know, that's where I spent time because it was fun. And then, yeah. All right, cool questions. Awesome. Problem number 3. You had x minus 3 on top. Again, 2 candidates, because when we use pre-calculus thing, so we have all of these. You're wondering if these are asymptotes. So you would say limit x approaches 5, let's say from the left. And then you have x minus 3. You have your x minus 5, x plus 5. And now nothing cancels. Right? Since nothing cancels, then it has to be an asymptote. Because there is no way for you to get rid of the 0 from the denominator. It has to be an infinity. So technically, if you are to plug a value, you would get 2 divided by 0. Right? You get 2 divided by 0. And 2 divided by 0 in the limit goes to infinity. And now this is a good point for us to stop and think why something that is divided by 0 goes to infinity. You heard that many times. Division by 0 can't happen. It is undefined and all of that stuff. So for that, I will need a piece of paper. Which Mark is law. And I think we beat that law. Yeah, we did. Good. All right. I'm going to divide 1 by infinity. What is division? Cutting it in half, right? And then, so you divide things by chopping them into smaller pieces. So as I cut this, if I divide by 2, I get these halves. So 1 divided by 2 is a half, right? See? So now I have this. If I'm to cut further, it's a quarter, it's an 8, it's a 16, and so on. So if I am dividing by infinity, I'm getting where? Where am I getting if I'm dividing by infinity?
Nothing.
I'm getting to 0, right? Because you see how physically it was this big, right? The paper was this big. When I divide only by 2, it's this big. If I take 1 and divide by 4, it's this big. Much smaller, right? If I take number 1 paper, divide by 8, it becomes this big. So the bigger number I divide by, the resulting thing is smaller. So if I divide by infinitely large, magic, nothing there, all right? So dividing by infinity will hit to 0. Now what happens if you're dividing by 0? If you're dividing by 0, it does not exist. The answer doesn't exist. In the limit, we say it's infinity, but to understand the physics, the physical reality behind it, I do that with markers. Just need to find right markers. There we go. So behold, 6 markers, which is 1 unit now. And if I divide by 2, right, that means create 2 piles, right? And keep assigning markers until you run out. So 6 divided by 2 would be 3. In each group is 3. And then you can divide by 3, right, get 3 groups of 2. Well, that one is lost forever. And then you get 3 groups of 2. Early exercise. And 1. There we go. 6 divided by 3 is 2. All this effort, right? So now you understand that division actually creates physical groups that were in the denominator. So when I said 6 divided by 2, that's 2 physical groups that exist. So 6 markers divided by 2 means you are creating 2 groups, and each group will have the answer, which is 3. So can you take one thing and divide it into 0 groups? You have that one thing. You can't go lower than that. That would make no sense. You can't stuff one thing into nothing. That can't be done. So you can divide one thing into nothing, but you can divide nothing by 1 or 2 or 3. So 1 over infinity is going to, I'm not going to put equal 0. It's going to go to 0, and this puppy will go into undefined, right? So we say infinity. So now you see that our problem, going back to our problem here, we see that we have this issue of a number divided by 0, right? So we can see that we actually have to graph this one, and we will see those vertical asymptotes pop up. Those infinities will pop up in case. Now, we're a little bit crippled on this problem because we haven't covered chapter 4 yet. So you technically don't know how to graph this without calculator. We are going to learn in chapter 4 how to graph this function, and then in that case you will be able to look at the graph and determine technically everything about the function, right? The main range and everything else. So for now, you will take my word for it. That's infinity. So yes, VA at x equals 5. And I'm just going to say same because I'm lazy. And you can fill it in. VA at x equals -5. So if you study these 3 examples side by side, compare and contrast them, you should be figuring out very quickly what's going on with these infinities and so on. And now to give you a little bit of application here. It's not done in textbook, but you might as well know. So you're all hopefully familiar with the fact that if you short 2 prongs on the outlet, you're going to create mini explosion. Why? How? Or if you short 2 ends of the battery, plus and minus. If you do that on the car battery, it's going to be a huge spark. If you do it on a small battery, it's a little spark and battery dies. Why? Why is it happening?
Overloaded the medium.
Well, here it is. It's this. So what we are going to do is we're going to first write down the Ohm's law. Current is equal to voltage divided by resistance. Now, current is the flow of electrons through the wire. The voltage is what's pushing it. Technically, that would be your batteries and stuff like that, like a source. And the resistance is your device that you are connecting, whether it's a cell phone, light bulb, or your hair dryer, whatever it is. Now, when you short something, that means that that resistance is going down to 0. So, think about it. You're plugging something into the wall where you have a constant 110. Usually you have 118, but you have 110 volts there, and you short it where the resistance is going down to 0. Now, what did we say? What's happening when you have denominator go to 0? Where's the current going to go?
It approaches infinity.
Yes. So the current is trying to approach infinity. So you see that as the resistance is approaching 0 because you shorted it, the current is approaching infinity. Now what do you have? You have that the current is proportional to temperature. So if the current is trying to go to infinity, then temperature is trying to go to infinity. And what's the explosion? Yeah, exactly. So you see what happens. It's a physical thing that is explained by exactly what we did here. You're creating a vertical asymptote, and with a vertical asymptote, the current is going to, on the graph, just shoot up. And the lower the resistance goes, the higher the current. So your wires in the walls will be rated, let's say, for 20 amps, 20, not infinity, all right? And then your fuse, right, circuit breaker, is also rated 20 for that line. And you plug way too much stuff, it's going to keep popping. And you keep resetting, and it keeps popping until you figure out that I need a bigger breaker. So you change breaker, right, which you shouldn't. You change breaker from 20 to 40, let's say, right? And it's not popping, but then the house burns down. And the house burns down because your wire is still rated on 20. You didn't change the wire in the wall. You have to change everything. If you want to keep that amount of use, you have to change the breaker, and you have to change all the wiring up to the outlet, and you have to change the outlet as well, because outlet is rated 20 as well. They all match. Right? When they build these houses, there is a code that says 20, 20, 20, 15, 15, 15. You can't just change one of those, because as soon as you push more current through the wire that is rated 20 and you're pushing 40, that goes up as well. And that's what burns the house. So, playing with these things, right, you have to know math. So I obviously understand the concept, so I know what to change, where to change, how to change, and what to do, right? If you're an electrician, you know the code, perfect, right? But you can't just go and say, okay, so this outlet says on it 20, so you just put a bigger outlet. No, right? Because your wires and everything else is still rated less. And you see how these things work. So that's a single application. There's just thousands of these things. Your charger's operating on a certain temperature, and then, they're warm sometimes, but they're never going to be, right? If they're excessively warm, something is wrong. But if they're just warm, that's their operating temperature, right? This is warm now, right? I'm using it, but it's not warm to the point where I can't hold it. So that's something that, that's the end of 2.4. We'll talk about vertical asymptotes. And the next one is 2.5 after the short commercial breaks.
I like those.